In this video, we're going to start to take a look at Green's theorem specifically and understand what Green's theorem actually says and why we might be able to actually believe that it's a true statement. So we'll provide a partial proof of Green's theorem. So let's take a look first at what Green's theorem is all about. What does it say? So here's what we start with. Suppose that C is a positively oriented, we talked about that in the last video, positively oriented, piecewise smooth, simple, closed curve. Okay, this makes the start of Green's theorem pretty intimidating because there are 4 different pieces of terminology that we have to know right off the bat in order to make sure that we understand even what this region C is. So it's got to be positively oriented, like we saw in the previous example. As I walk around that curve, my interior region has to be on the left side. It's got to be piecewise smooth, so each of the pieces that maybe build this curve have to be smooth curves. It's got to be simple, the curve can't cross over itself, and it's got to be closed, it's got to start and stop at the same point. Okay, so if I have a positively oriented, piecewise smooth, simple closed curve in the plane, and D is that interior region that's bounded by C, then I can state the following. If P and Q are 2 functions that have continuous partial derivatives on some open region that contains D, then I'll see here that there's going to be a relationship between this work integral that I have over on the left, this line, well, work integral or line integral, but I have a line integral over here on the left related to this double integral on the right. Okay, so we're going to try to see what this relationship is all about and how would I actually go ahead and justify this relationship. But before I do that, I want to go ahead and note why exactly we care about Green's theorem. The advantage of this is, notice, to say that if I understand how to compute, or if I don't quite understand how to compute maybe this difficult line integral, I can instead opt to evaluate a double integral. So that would be like the volume under the result of this subtraction over the region D that's enclosed by my curve. So it's allowing us to skip the work of doing a line integral and instead doing the work of hopefully a simpler double integral. Now, let's take a look at why exactly Green's theorem might even possibly be true. The proof in general is fairly difficult, but we're going to go ahead and try to prove just a special case where, as I state here, D is both a type 1 and a type 2 region. We'll refer to these regions as simple regions, typically. So let's take a look at what we have here. So here's where I'm going to start. Okay? So I'll say that we first note that if we can show that my integral over C of p dx, so that's kind of just part of this line integral. If I was able to show that this was equal to negative double integral of D for partial of p with respect to y, and if I was able to show that my line integral with the q, so that's that second part over there, if I was able to show that that was equivalent to a double integral, partial q with respect to x, if I was able to show that these things are equal, then I can definitely reach this conclusion pretty simply. Because notice, if I add the 2 left-hand sides together, I create the left integral. And if I add the 2 right-hand sides together, I create this other integral. So really, if I can show these 2 things, then I'll actually be perfectly good. So if I can show these 2 things, we will have proven what we desired. Okay, so this is going to kind of be our goal, to show these 2 facts. And actually, I'm not going to go ahead and try to show the first one. I'll leave the second one as something that you could try to do on your own time if you're interested. Okay? So let's take a look at what we have down here on the next page. So let's go ahead and remember that we're going to consider this special case where D is both a type 1 and a type 2 region. So I'll start by saying this. I'll say, since D is a type 1 region, we know that we can express d as, and I could kind of define it in the following way. I could say that d is going to be equal to a set of all possible x, y's, where my x values are just bounded between some numbers, and my y values are going to be bounded between two functions. So I'm going to call that g1 and g2. Okay? To kind of get a picture of what I might be working with, maybe we'll draw something kind of like this. So let's suppose that down here I have A, I have B, okay? And maybe I have something that kind of looks like this. Okay? I'm going to have maybe these two edges of my region, and maybe I kind of have like something like this that kind of maybe connects the dots up top, and maybe I have something down here that kind of connects on the bottom. So maybe this bottom function down here, I could refer to that as, this is my g1 of x, notice because that's the bottom value for y, and up here maybe this top function is g2 of x. So this is possibly what the region D might look like. Okay? So again, I'll kind of refer to this whole space in here. This is my region D. Okay. Now, I can easily go ahead and see here that if I have something like this, the curve around the outside has to be my C. And if it's going to be positively oriented, then that means that it would have to be oriented kind of in the following way. And I'm going to go ahead and label each one of those individual sides with a different C subscript. So maybe call this bottom side C1. I'll call this right side C2. The top I'll call C3. And the side maybe I'll call C4. And all together, that's really just going to be C. Okay, so this is a possible region that I could have. It's also possible that these sides here could be a little bit smaller, or maybe even shrink all the way down to a point, right? Because if this point right here connected with that point right there, automatically, like they butted up right against each other, then I would still have my y as a g2 on top and g1 on bottom. Again, our goal right now is to say, if I have a curve like this, can I show that maybe this line integral of the p dx is going to be equal to this negative double integral over d of partial p with respect to y, dA. All right, so let's see. Maybe I can start by dealing with that double integral. So I'll say, oops, and let me switch back to my black here. I'll say that we note that if I was going to do a double integral over d for partial p with respect to y, dA, I can easily go ahead and start to set up how I would go ahead and compute that. It's not too terribly difficult, because I can already see that I understand my bounds. I would integrate from a to b, from g1 of x to g2 of x, and then I'd have my partial in there, and of course that's dy dx. So if I wanted to start integrating, I would say, okay, well this isn't too tough. Notice that if I have a partial derivative right now with respect to y, and I do an antiderivative with respect to y, that's just going to take me back to just the function p, which again might have variables of x and y, and now I just want to evaluate that from g1 to g2, and after I do that, I'll integrate with respect to x. Okay, so if I continue with this, notice that if I was to replace my values of y with these new functions of x, I would get something that looks like the following. My g2 would go in place of my y. My g1 would go in place of my y. And I would have all of this, which now has a dx on it. And I need to move this stuff up here at the front, because I also need to keep my integral on here from a to b. Okay, of course then, if I take a look at this, this is fairly complicated, and I could start to think about how I might potentially attempt to integrate with respect to x, but I'll realize that's very difficult since this p function now has a bunch of x's in it. I don't really know what it looks like. It was really easy to integrate with respect to y here because I already had a partial derivative. So for the moment, we'll just pause right here. This is something that we can note right from the beginning. We can definitely see that whenever we come across this guy, it is equivalent to all of this. So let's note a couple other things here that we could definitely say. Okay? I'll also state this. We also note that the x-coordinate for C2 and C4 is constant. So take a look at the curves up here, right? These are both vertical lines that I have right now, and so the x-coordinate along them is constant. So I can easily see that for C2, I know that I have x is equal to b over there for that particular curve. And of course, what that can definitely tell me is that if I wanted to take the derivative of this, I would get 0 dt. If I took the derivative with respect to t, like I was getting ready to set up a line integral, I take the derivative both sides, I'm going to get dx is actually equal to 0 dt. And for C4, notice I'm going to get something very similar. I have x is equal to a, but that gives me that dx is again equal to 0 dt. Thus, when I think about a line integral along C2 for my function, p dx, I'm going to realize that that is exactly going to be the same as what I'm going to get when I go along, when I go along C4, because both of those, notice if I replace my dx value with a 0 dt, then my entire integral is just going to turn into 0. So I can see that the line integral, again, that I'm interested in computing is this line integral around the entire thing for p, and I can tell that at least along these two sides, that line integral equates to 0. So let's figure out what the line integral is going to be along the other two sides. Okay, so we'll state this. Now, a parameterization for C1 could be given by a function, let's call that R1, and that's pretty easy to create a parameterization for. I could create a t comma g of t. Notice that if t then acts like the x-coordinate, g of t will automatically tell me the y-coordinates. And of course here, this would be where t goes from a to b. And so, I can easily see then that the integral along C1 for p dx is going to be equal to an integral from a to b of p, and I would just have to replace in my x and my y. I have to substitute those in for what I have. Notice that if I was to replace my dx at the back, that would be the derivative of t, so I'd have 1 dt. Notice that in the same way, I could say that a parameterization for C3 is, well, let's call this R3, and this is going to be t comma G2 of t. Oops, this one up here should have been G1, indicating that I was on the bottom. And where t again goes from a to b. Now, one small adjustment needs to be made here. Notice that I didn't ultimately create a parameterization for C3 exactly, because C3 is supposed to start at this value of b in the x direction and move back towards the value of a. So what I've really found a parameterization for right now is negative C3. But that's okay, because what that tells me is that if I was to do the integral along negative C3 p dx, I get, again, an integral that goes from a to b P of t comma g2 dt. So I can kind of see now that I've been able to create, ultimately, an integral for C4 along C2, C1, and negative C3. So if I was to kind of combine all this information, let's say if we combine all of this, we see that if I wanted to integrate p dx across all of C, that would mean that I would have to go across C1, and then across C2, and then across C3, and then across C4. But of course, since I found what each of these things are, I can go ahead and start to substitute them in. I know that the C4 and the C2 will turn into 0, and I know that the C1 and the C3 I should be able to substitute in some stuff for. So notice here I'm going to get for C1 the following integral. And then in place of C3, I don't really have C3, but I have negative C3. And you might remember that the relationship between that is that this is the same as just saying it's the negative value of what I get when I just do regular C3. So I can swap this out for the following. Instead of adding, now I'm just subtracting since I'm moving along the negative curve. Of course, though, if I was to simplify this down, I could see that I could combine this to actually just be one integral of a larger function, p of t g1 of t minus p t g2 of t dt. But of course, if I was to go ahead and take a look at this, I can see that there's a couple other things that I could begin to do. First off, I could recognize that if I was to go ahead and simply, I'll actually write this on the next line. But if I was to go down here and pull a negative out of the inside, I could reverse the order in here to have my g2 function come first, my g1 function comes second, and then I can simplify all of that down to actually look like, again, something that we've already seen. That looks like this. Notice that this integral here is exactly the same as the integral that we had up here in red. It's a perfect match. And so we can easily say that if that original red integral was equal to this, then we know that we should be able to say that it's equal to that. But if I look at then what I've linked together, I've been able to argue that this integral along C of p dx is indeed the same as this integral for this negative double integral, the partial of p with respect to y dA. In fact, that's exactly what we were hoping to show right from the beginning. So I'll go ahead here and just kind of wrap this up by saying that a similar argument can be made to show that integral along C of q dy is going to be equal to the double integral across D with partial of q with respect to x dA. And I'm actually going to leave it to you, as I mentioned at the start of the video, to try to go ahead and justify this to yourself. Okay? Proving Green's theorem in general is actually a lot harder than what we did here. Again, we only did a special case. To prove in general, we'd have to be able to show that technically the region D could always be decomposed into a bunch of smaller, simple regions. So in the next video, what we'll do is take a look at some additional notation and how we can actually put this to use in a specific example.